Good afternoon, everybody. Welcome to another exciting afternoon of Chem 1105 with your host, me, Dr. White. Hi, everybody. All right, let me remind you, tomorrow, Thursday, at 8 a.m., I'll send out a password email with a password for the password protected PDF file for test number 1. You'll have until Friday, 4 p.m. to upload test number 1 answers to the assignment area Blackboard as a single PDF file. I have files in there. No, it's not visible yet to you. I have files how to do that, just like in the labs. Also, in the assignment area for test number 1, there'll be the periodic table, the green one that I'm using. That's the one you should use for test number 1. All right, that's one thing. I got my list of things to do here, talk about. All right, another thing. A little while ago, I sent out an email with a link to a video for what I have created a while ago that eliminates test anxiety. I've thought of different names, and the only thing that seems to stick is it's called the method. And it's the method to reduce test anxiety. And over the years, I've had a lot of students, a number of students who have test anxiety. What that means is they study hard, but when they sit down and take a test, their brain goes, whoop, and they just do awful on the test. And once they learn my method to eliminate that test anxiety, their grades go from here to here. I've had students go from getting D's and low C's to high A's. You still have to study, but this really helps. And you can use it for other classes, and you can use it for other things too. So use that link, watch the video. If you have trouble mastering it, see me after class, come to my office hours or email me, and we can always set up a special Zoom meeting so I can help you out. But it's amazing how well it works helping students. All right, another thing, don't forget to hand in labs. Labs are a lot of your grade, and they're easy points. You got to hand in a lab. You got to do it too. Don't forget, when you hand in a lab, have a selfie. I guess you go like this or like this. My old phone, the button was up here. The one I have now, a Galaxy, Samsung Galaxy, the button's right here. So don't forget to do a selfie with you and something from that lab, some piece of equipment, or you mixing some, whatever. Because if you don't, I have to give you 0 points. That's the Department of Chemistry rules now for home labs, that if you hand it in, you also have to have a selfie, except for 1 or 2 where there's no thing, you're just writing out things. You're not really doing anything with stuff from the kit. I think there's only 1. All right, let's see, I got selfie test number 1. All right, one other thing, I looked at the syllabus a little while ago. I realized, oops, no, I shouldn't have had a V8. Oops, I made a mistake. As you know, let's take a look. Today's the 28th, and next week, Tuesday, is July 4th. Yay! Happy July 4th coming up. And if you look at my syllabus, I have a lab scheduled for July 4th. No way, there's no class. It's a holiday. So the lab that is originally scheduled for July 4th, can't do that because it's a holiday, I will do on Monday, July 3rd. The lab for July 4th, I will do on Monday, July 3rd. I always do that with some holidays. I write my syllabus and forget, oops, it's a holiday. There's no school. I think I already did that this year, this summer on, what is it, June 19th. I probably pronounced it wrong. That holiday which is now a federal holiday, which I shouldn't have forgot. Bad Dr. White, bad Dr. White. All right. I think I've covered all the announcements, so let's get back to work. Oh, by the way, here's where I made the mistake. You'll see lab number 7 on Tuesday, the 4th of July. Nope, I'll do this lab number 7 on July 3rd when we'll still have class. All right, now yesterday I was talking about the VSEPR theory. Remember, click switches off. And the VSEPR theory is based on the pairs of electrons that are bonded and non-bonding, the valence electrons of a molecule. They want to be as far apart as from other pairs as possible. And wrong button. And as I showed you yesterday, this chart, if you look at number 4, which is most of the molecules, depending on if A in the center an atom has X, which are other atoms bonded to it, it would be tetrahedral. There are only 3 plus a non-bonding electron, which is a pair of electrons E. It would be trigonal pyramidal. And finally, if you had 2 atoms bonded to the center atom A, and you had 2 non-bonding pairs of electrons, these 2 E's, it's bent. By the way, this bent shape you see, that's the shape of water. The 2 white balls are hydrogen. That pink color, I guess it's pink. My sisters say you don't know your colors. Well, I know red, green, and blue, but whatever, that it's not really purple, maybe wine colored, that's the oxygen. And here, similarly, the center, the wine color, it would be nitrogen, and the white balls would be hydrogen and ammonia. And here, tetrahedral, that center wine colored. I like that wine. My wine doesn't look like that, even though I love red. Sort of like red wine, but I'm a white wine person myself. Dr. White, white wine. Yes, I do. By the way, I like German white wine the best. Pierce Porter, Golden Shock, and Cabernet, or Spätlese, or Auslese. But anyways, this tetrahedral, if the center is carbon, those 4 balls are hydrogen, that's methane, natural gas, the stuff you cook with. So molecules have shapes, and it's very important to shapes. It affects certain things in our daily life. In fact, the shape carbon atom forms affects the shape of our RNA and DNA. Yep. Well, anyways, that's the VSEPR theory. Let's move on and talk about a couple other aspects of covalent bonds. And one is electronegativity. That's the ability of an atom to attract electrons to itself. And if you look at the periodic table, electronegativity of an element increases when you move from left to right and from bottom to top. Let's take a look at a periodic table. So here's a periodic table. And by the way, switches off on this, but it's still useful information that I'll be using later on in the semester. Remember, material I'm talking about now will be on test 2, not test 1, but this one, click, switches off. Now, when you go from the left to the right, the electronegativity increases. Oxygen has a higher electronegativity than hydrogen, which is quite important in our daily life. And as you go from the bottom to the top, the electronegativity increases. Fluorine is more electronegative than chlorine. Chlorine is more electronegative than bromine. What does this electronegative mean? Well, assume you have two atoms here. One's strong and one's not that strong. And they're sharing a pair of electrons. And the strong air atom says, let's share them closer to me than you. And the one that isn't as strong says, well, you're stronger. Okay. It's sort of like if you have an older sister and you're out in a rainstorm with one umbrella and you hold the umbrella over both people, but it's more over the bigger person. Don't tell my sister I told you that story. That happened when I was about 6.5. I got sort of wet, but not completely. She was more electronegative. So this electronegativity means when you have a bond, if they're the same, you have equal sharing. If there's not the same electronegativity, the electrons are held a little closer to the stronger atom or element. And again, switches off, click, sort of like the light switch. You can't see right. Oh, it's right there hidden. But anyways, when you move from left to right, more electronegative, and bottom to top, more electronegative. So this affects the type of covalent bonding. Switch is still off, next couple of slides. When they're equal electronegative negativities, we call that a nonpolar covalent bond. That's a covalent bond between atoms with identical or very similar electronegativities. They're both the same strength. So they say, let's share equally because you're not stronger than me and I'm not stronger than you. Now, when they are unequal, we call that a polar covalent bond. And that means the electrons are a little closer toward one atom of the bond. And this forms what's known, click us off, a dipole. Di means two, pole, poles are charges. And it's a polar bond that has a separation of positive and negative charges. The charge separation is only partial. It's not a full charge separation like an ionic bond, since they're still sharing. And we show this by using the Greek letter lowercase delta and putting a plus or minus next to it. Now, here they say occur when dipoles can't cancel each other out. Let's look at water. This is very important. Now I'm going to turn the switch on for water because this is an important aspect of water that affected how we are on this planet. Really? Yep. Now, if we consider water HOH, which is really H2O. Now here, the line is a pair of electrons, and that's the way organic chemists do. If I did Lewis structures, I'd have dots. Now, because the oxygen is more electronegative, for this bond, it says, I'm stronger than you. Let's have the electrons a little closer to me. And they do. And because of that, there's a slight negative charge on the oxygen. Remember, delta like this means slight difference. Capital delta in math and also chemistry, real difference, regular difference. But this means little difference. Hold on 1 second. I apologize. They hung up on me. Well, I'll leave a message. All right, we're talking about on oxygen because the electrons are closer, being held a little closer because oxygen is more electronegative. Hold on, let me try again. I apologize. I apologize about that. It was my dentist's office. He had to cancel my Friday appointment and they moved it to Saturday. Thank you for being patient. All right, let's try and do this again. All right, we look at oxygen, it's more electronegative. And because of that, thank you, Yulia. All right, because of that, there's a slight negative charge because the electrons are a little closer to the oxygen because it's stronger. Well, if that happens, there's a slight positive charge on the hydrogen. And it happens to the other hydrogen too. So there's this charge. Now let's look at a molecule. Let's make it more bent, which is really how water is. Now let's have another water molecule. Remember, water is H2O, which is what this is. 2 hydrogens, 1 oxygen. Guess what? The same thing happens. This has a slight negative charge, and the hydrogens have a slight positive charge. Well, it turns out opposite charges attract. And because this is a slight, and that's why we use the delta, lowercase right here, it's not a full ionic bond, but there's a very tiny weak attraction. And remember, oh, hold on. Let me get more subtle. Know this. Now, there's a slight charge attraction here. And this slight force holds the molecules of water together differently than other molecules. And this force is so important, it's called the hydrogen bond. Now, it's not a full chemical bond, it's a weak force, but it's strong enough to make a difference. Well, what kind of difference, Dr. White? Well, let me show you. See this bottle? It's got water in it. And guess what? It's a liquid. Now, molecules with similar, and it's a concept I haven't taught, I'll teach you later on, called molecular weight, have similar what's called boiling points and melting points. Boiling point is the temperature at which a molecule or a compound will boil, go from a liquid to a gas, and we'll talk about this in detail later in the semester. But right now, molecules with the similar molecular weight of water, H2O, are gases at room temperature, a gas. But water is a liquid. It should be a gas at this, based on its molecular weight, but it's a liquid. And why is it a liquid? Because of hydrogen bonding, that weak little force that holds the molecules together. Think about our planet. What if water at this temperature was a gas? Well, we wouldn't have blood like this. Our bodies wouldn't look like this because the water, which plays an important role in our bodies and our planet, would be a gas. But no, it's a liquid. That's why we have oceans. That's why we have water we can drink as a liquid. And we have vessels in our arms and throughout our body that carry blood, which is mainly water, which is not a gas, it's a liquid. So think about that. That tiny little force between the water molecule. Can you see those water molecules? Yeah, you can't. You don't have X-ray vision. Guess what? I don't either. I'm not Superman. You see, no red S there. But anyways, that's a very, very important concept. And let me talk about it again, because hint, you should know this. See, I'm drinking some of that water that's hydrogen bonded. Now let's go through this again. Because of the difference in electronegativities is the strength of an element or atom to hold on to electrons. And as you go from left to right and bottom to top of the periodic table, you get more electronegative atoms. Good question. One of your colleagues just asked, will plastic bottle react with water? And the answer is no. Now, sometimes there's certain additives on bottles, maybe not plastic, well, yes, plastic, that are not part of the actual plastic. I mean, it's a good question. Now, when you make plastic, sometimes there's materials that haven't fully reacted, and they might leach into the water. With the actual bottle material, this stuff, which is PET, polyethylene phthalate, it won't react. Now, a number of years ago, they were made baby bottles, especially not water bottles, but baby bottles with a chemical called BPA, bisphenol A. And there was still some bisphenol A on the surface that was unreacted in those bottles. And that would get into people, mainly babies, baby bottles. And bisphenol A, and I'll talk about it later in the semester, mimics a certain one of your hormones and can mess things up in your body slightly. And a number of years ago, because mothers were complaining about that, one company made a decision that helped the whole country, maybe even the world. And that country was Walmart. And Walmart said, we will no longer sell baby bottles made from BPA. And because they were the country's largest seller of baby bottles, all the companies who made baby bottles had to come up with new formulations. But this type of bottle, unless you boil it, and even then I don't know about that, but you're not going to boil this water in this bottle, put it in boiling water, or put boiling water in here. I wouldn't. But regular water under this, or I have it came from my refrigerator, so it's nice and cold. No, nothing's going to leach from there that's going to hurt you. And thank you for your question. Isn't it nice you have an instructor who knows the real world of chemistry? Don't answer that. All right, well, let's get back to hydrogen bonding. Again, quick review. The oxygen is more electronegative than hydrogen. As you can see, hydrogen's all the way over on the left, the low electronegativity. Oxygen's way over on the right, higher electronegativity, stronger. And there's a slight charge differential because oxygen holds the electrons they're sharing a little closer to it than the hydrogen. And we show that by the lower Greek delta, which means little or small difference. And water, the hydrogens have a slight positive charge and the oxygen has a slight negative charge. Now, water is a bent molecule. And when you have two molecules of water, you can form, there's attraction between the slight positive and slight negative, a hydrogen and oxygen. And that's what I'm showing here with these little dots here. Let me redo this in red. It'll look nicer. And if I had more water molecules, this would attract too. And they contract from either the hydrogens or both. And that slight attraction, you should know, is called the hydrogen bond. And hydrogen bonding is responsible for why water is a liquid at room temperature. And there are other things I'll teach you this semester that hydrogen bonding helps. And hint, you should know this. All right, let's move on. Oh no, guess what? We're done with chapter 4. Yay, we're done with chapter 4, which means I think Wednesday we'll do part 1. Let's see what practice problems I have. Do I have it separated or not? Nope, we have it all. I thought I did, but I wasn't sure. Next Wednesday, I will go through chapter 4 practice problems. I highly recommend you do them before I do. You have to keep up. Summer is a faster pace. All right, we finished chapter 4 because we've already done part 1. We just finished part 2. Guess what time it is? Yes, it's time for a new chapter, new stuff. And that chapter is chapter 5, part 1, or part 1 through part 4. Remember, because the way the book is written, I'm jumping around on some of the chapters. It makes more sense the way I'm doing it. Hope you agree. Uh-oh, I got to open up chapter 5. Let me do that. Now I've got it open. Let me show it to you. And here's chapter 5, and it's called Chemical Accounting. And remember, this material will be on test 2, not test 1, which I'm giving tomorrow. Again, this will be on test 2 later on in a week or so. All right. Now, when we talk about chemical change, what is that? And I'll never ask on a test what's a chemical change, but I'll use that term. So what does it mean? That's when an original substance is converted to a new substance that has different composition and different or new chemical and physical properties. So when you change an original substance into something new, we call that a chemical change. Now, changes occur during what we call a chemical reaction. And a chemical reaction which shows you the chemical change, the original substance or substances change to new substances with different physical properties. And the lab you did yesterday, you're going to do today if you haven't done it, or tomorrow. Remember, I extended it. It's not due Thursday. It's due next week. I think through Wednesday because it's a lot of work. And also the July 4th holiday is coming up. Yay. Ooh. As soon as I finish this, I need to talk about something. All right. Now, maybe after the break, I'll do it. The original substances change to new substances in a chemical reaction. Now, this I'll never ask on a test, but you have to learn this for yesterday's lab. How do you know visually for my class, since usually this is mainly inorganic reactions, but some organic reactions too. How do you know there was a chemical reaction if you don't have modern electronic equipment that will tell you that? Well, one, if you see a change in color, major change in color, that indicates there's been a chemical change. If you see formation of gas, meaning bubbles, that means you mix two things together and all of a sudden you see bubbles, and neither one has bubbles in it, then that means there's a chemical change. If you see the formation of a solid, which we call precipitate. Remember, I showed you yesterday the snow globe with the snowman. If you shake it up, my sisters had those. They're pretty. And you shake it up and the white particles come down, look like snow in there. Well, chemists would call, oh, look at the precipitate in there. And finally, if you see a change in temperature, this is evidence of a chemical change. Now, for this slide, click, switches off. I'll never ask questions on this in a test, but you did the lab yesterday, so you should know how to do this for the lab. Now, how do we show when we communicate to other chemists or other people a chemical reaction? And we use what's called the chemical equation. I'll never ask what is a chemical equation, but I'll use the term, so I should define it. A chemical equation is a written statement that uses symbols and formulas instead of words to describe the change that occurs in a chemical reaction. And so the chemical equation describes, using shorthand, symbols and formulas, the change that occurs in a chemical reaction. Now, the next slide and the one after it are going to have some important concepts. I will never ask what are the conventions used in writing chemical equations, but you should be familiar with this because it's important. All right, when you write a chemical equation, the correct formula of the reactants and the starting materials are always written on the left side of the equation, and the correct formula and products are always written on the right side. Let's take a look at this. Let's say I have this chemical equation, and I'm not even going to use any formulas right now. All right, this is a chemical equation, and it says A plus B. That means you mix A and B together. Then you have that arrow, and at the head of the arrow, you make C and D. Oh, I better be subtle. And what you should know is the following. At the base of the arrow, these are called the reactants. At the base of the arrow, A and B are the reactants of this chemical equation, which is a chemical reaction. And that means you mix the two together to make a chemical reaction. Now, since I have many decades experience in the chemical industry, we also call them starting materials. And that will slip out often. So A and B are your reactants, also known as starting materials. At the head of the arrow, this arrow, these are always the products or products if there's more than one. In this case, C and D are the products, A and B are the reactants. So you react A and B and you make C and D. Now, the plus sign in a reaction chemical equation is the word and. That's how we write the word and. We just use a plus symbol. So what this chemical reaction, this chemical equation for this chemical reaction is A and B react together to make C and D. A and B are your reactants. C and D are your products. Now, the reactants and products are separated by an arrow, and the arrow always points toward the product. And plus signs are used to separate different reactants or products, which again, here, A and B, and the plus side means and, this separates the two, are the reactants. They're at the base of the arrow. The head of the arrow, where the point is, the pointy part, in case you don't know, this is the head of the arrow, which I use another arrow to show. Wow, that's so profound. But anyways, at the head of the arrow are always the product or products. And you should know this. Well, let's try something out. Let's look at an interesting chemical reaction. And the equation for that reaction is this. Now, later on, I'll teach you about how to something called balancing this equation, but let's look at this equation. All right, your turn to have some fun. What are the reactants of this chemical equation? What are the reactants of this chemical equation? Your turn. Boy, that was fast. I didn't even have time to drink any of the water that I just made. All right, what are the reactants? At the base. So the reactants would be hydrogen and oxygen, gas. All right, what is the product of this reaction? Your turn. And you're done already. See how easy chemistry is? And the product is at the head of the arrow, and the product of this reaction is water. And the reactants are hydrogen and oxygen gas. Remember, at the base of the arrow are the reactants or starting materials. At the head of the arrow are the product or products. And thank you for everybody who's answering questions. Thank you. Now, I've already talked about this, the convention. Now, there's a validity check. And when you write a chemical equation, it must be consistent with the experimental facts. That means if I had mixed hydrogen and oxygen together and got something else, I wouldn't have put down water. But if you do that, you do get water. And there's something called conservation of matter. And that means there must be the same number of atoms of each kind on both sides of the equation. This is very important. Conservation of matter means in a chemical reaction, you never create or destroy atoms. You just swap them and change partners if they were partnered with something. And the same number and same type of atoms has to be on both sides, the base and the head of the arrow. And this is a balanced chemical equation. It has the same number of atoms of each element involved in the reaction on each side of the equation. Now, as I said earlier, like about 35 seconds ago, or maybe 60 seconds ago, atoms of elements are never gained, lost, or changed into atoms of other elements during a reaction. All you do is swap partners. So let's look at this reaction. Hydrogen gas plus oxygen gas makes water. And the question is it balanced? And the answer is no. How do I know it's not balanced? Well, here on the reactant side, I have two hydrogen atoms right there. I also have here two oxygen atoms. Now on the product side, I have two hydrogen atoms, but only one hydrogen. And there should be the same number and same type on both sides of that arrow, and they're not. And to change that, you have to balance the chemical equation. And if I look at the time, I think this would be a good time to take a 5-minute break. Let's take a 5-minute break. I'll come back and we'll continue on with balancing chemical equations and my special advice how to do it easily. Shh, don't tell anybody I'm giving you these special advice secrets. Shh. See you in 5. I'm back. Profound. All right, let's continue on. Now, before I go back to what we were talking about, balanced chemical equation, let me remind you tomorrow, test number 1. Remember, tonight I have office hours, so if you need any help, stop by 7 to 8 p.m. on Zoom, so you don't even have to get into your car to get help. Just turn on your computer and log in. Also, don't forget, I sent out an email with a link to a video which teaches you my method that I created, how to eliminate test anxiety. And it works really good. And it's helped a lot of students over the years. All right, let's get back to balanced chemical equation. So it's important in a balanced chemical equation, you have to have the same number of atoms, excuse me, of each element involved in the reaction on each side of the equation. Now, let me skip forward to this slide and we'll come back. There's something called the coefficient. I will never ask you what the coefficient is, but that's a number that's placed to the left of the formula of a substance that changes the amount, but not the identity of a substance. And this is very important. The coefficient is always a whole number, never a fraction or never a number with a decimal point. So let's go back and look at this reaction. And that is H2 plus O2 makes H2O, and it's not balanced. So how do we balance this equation? Well, we have to have the same number of atoms of each type of atom on the same side of the arrow. Now, the problem was oxygen. There are 2 oxygen here, but there's only 1 oxygen here. How do I make this 2? Well, I can't change the formula. This is another molecule. This is called hydrogen peroxide. And that's not what we're making. We're making water. You cannot change the formula, but you can change how many. And if I had 2 of them here, this is the coefficient. And now 2 times 1 tells me there's 2 oxygen. But I now have more hydrogens. 2 molecules, each molecule has 2 hydrogens. 2 times 2 is 4 hydrogens. Well, this side only has 2 hydrogens. What do? Well, you change the coefficient. You want 4 hydrogens on both sides. Therefore, I'm going to change the coefficient. And lo and behold, we have 4 hydrogens. Now let's find out, is it balanced? How do you check if it's balanced? You look at the atoms and the number of atoms, the type of atoms on each side of the arrow. That's a messy arrow. Let me fix it up. You look at both sides of this arrow. On the base or the reactant side, we have 4 hydrogens. On the head of the arrow, the product side, we have 4 hydrogens. Looking good. On the reactant side, we have 2 oxygen. And on the reactant side, product side, we have 2 oxygen. So this is now balanced. And the balanced chemical equation is you take 2 hydrogen atoms. When there's no number in front, the coefficient is 1. React with 1 oxygen or 2 hydrogen molecules, react with 1 oxygen molecule to make 2 water molecules. And now it's balanced. Yay! Now, an important thing is the coefficient should always be the lowest ratio. If you can divide the coefficients, all of them, by one number and get a whole number in front, you should. You shouldn't be able to divide the coefficients by the same number to get whole numbers. What I mean by that is we could have this. And if you notice, I have 8 hydrogens. 8 hydrogens. How do I get that number? 4 times 2. 4 times 2. And this side, 2 times 2, 4 oxygen. And here, 4 times 1, 4 oxygen. And you say, well, Dr. White, 8 hydrogen, 4 oxygen. Isn't that balanced? The answer is no. The convention chemists use, or I should say the rule, if you can divide all the coefficients by a number and get a same number, then you should. You should not be able to divide it by. Notice I can't divide these coefficients by a number to get a whole number. That's the correct balance equation. But if I divide each of these by 2, I would get this. So on a test, this, whoops, wrong color, right color. That's wrong, because there shouldn't be multiples of the coefficient. So that's something to watch out for. It's a common mistake students make when balancing chemical equations. Oh, this is fun. Let's do another one. Ooh. If you take sodium metal, react it with chlorine gas, guess what you get? Sodium chloride, which is table salt. Do I have time? Oh, I do have time. If you look at sodium chloride, NaCl, if you ever go out to breakfast, lunch, or dinner with a bunch of chemists, and I'm going to have to admit, I've done this more than once, more than twice, lots of times. One of the chemists will say, can you please pass the NaCl? They won't say salt, they'll say NaCl. And notice if you pronounce NaCl, NaCl. I hope you enjoyed that story. It's true. But anyways, is this balanced? And the answer is no, because you have 2 chlorine atoms on this side, 1 on this side. How do you balance it? Good question. Thank you, Dr. White. Well, if I have 2 chlorine here, how do I get 2 chlorine here? You can't do this. Students like to do this. This is wrong, because there's no such molecule that exists like this NaCl2. It doesn't exist. And I'll bet money on it. Did I tell you, if I ever say I'll bet with you, I've already known I've won. I don't like to lose bets, which is why I'm very careful when I say I'll bet. But we can't change the formula, but we can change the coefficient. How do I get 2 chlorine on this side? I change the coefficient to 2. And now I have 2 chlorine, but I also have 2 sodium. How do I get 2 sodium on this side? That's right. You change the coefficient. If I want 2 sodium, 2 times 1, I have 2 sodium. Now, let's see if this is balanced. Well, there are 2 sodium on the reactant side, 2 sodium on the product side. There are 2 chlorine. Remember, this means 2 of these, 2 chlorine on the reactant side and 2 chlorine on the product side. Sort of like balancing your checkbook, which is something I hate to do. But anyways, it's balanced. Yay, we've done it. You know something? I've been hogging all the fun. And why don't you balance this one? Your turn to have some fun. And when you're done, don't forget to say yes. One thing I should be clear, it looks like an N, but this is an R for bromine, BR. Sorry about that. It sort of looks like an N. There, it looks like a. You have to get used to my R. Looks like an N sometimes. All right, my turn. Everybody's done. Now, is this balanced? Hold on. Let's take a look at this. There's 1 potassium, 1 potassium. There's 2 bromine. Uh-oh, there's only 1 bromine here, so it's not balanced. How do I get the bromine on this side? I need 2 bromine. I can't change the formula, but I can change the coefficient, the number that goes in front of the formula. And that tells me now 2 times 1, 2 bromine. But 2 times 1, 2 potassium. Uh-oh, on this side, I only have 1. How do I make it 2? There's no such thing as this. No, there's no such thing. So I can't change the formula. Students like to do that and I mark it wrong, but I can change the coefficient, the number in front. I need 2. There's 1 here. 2 times 1, there's now 2 potassium. And if we look at this, let's check, and this is an important thing to do, especially on a test, 2 potassium, 2 potassium, 2 bromine, 2 bromine, everything's accounted for. You have the same number and same type of atoms on the reactant side as the same number and same type of atoms or elements on the product side. And it's balanced. Now, C3H8 is propane. That's the stuff in the white tanks for your barbecue. And if you react it with oxygen, you get carbon dioxide, water, and you get heat. That's the fire, but that's not in the chemical equation now. So is this balanced? If I look real quick, I can see 3 carbons and only 1 carbon. So it's not balanced. Now, I've been balancing chemical equation a few more months than you have. That's an understatement. A few more years than you have? How about a few more decades than you have? Yep, been doing them that long time. And I'm going to give you some advice. You don't have to follow it, but it makes your life easier on a test. and helps you get the right answer on a test. And that is when you're balancing chemical equations, leave oxygen and hydrogen last. When you're balancing chemical equations, leave hydrogen and oxygen last. And it makes your life so much easier. Trust me, I'm a doctor. Did that work? How about trust me, I'm an organic chemist? Did that work? How about trust me, I'm your teacher? Does that work? Well, I hope it did. Seriously, leave hydrogen and oxygen last. Let's take a look at what that means. Now, here we have this equation, chemical equation for the reaction of propane and oxygen gas, O2, to make CO2 plus water. CO2 is carbon dioxide. It's not balanced. So I'm going to follow my own advice and do hydrogen, oxygen last. If you notice here, we have 3 carbons on this side. We only have 1 here. How do I get the 3 carbons on this side? I put a 3 in front. Again, I started with anything but oxygen, hydrogen. I'm going to leave those to last. So I had 3 on this side. Now I have 3 on this because I changed the coefficient. You can't change the chemical formula. That's wrong, and I'll mark it wrong. All right, now all we have left is hydrogen, oxygen. So if I start here, I'll do hydrogen next. I could have done oxygen. Here we have 8 hydrogen. Well, there's no hydrogen there, but right there are 2 hydrogen. No, I need 8. So what do? 2 goes into 8 4 times. 4 times 2, I now have 8 hydrogen. All right, all I have left is oxygen. This side has 2 oxygen. But this side, you have to count up all the oxygen atoms from all the molecules on each side. So on this side, how many oxygen? Well, here we have 3 times 2. That's 6 oxygen. Here we have 4 times 1. That's 4 oxygen. Add them together. On this side, as it's written, I have 10 oxygen atoms. How do I get to 10 on this side? Well, there are 2 oxygen atoms for each oxygen gas. 2 goes into 10 5 times. And now, and let me five times. And now 2 times 5 is 10. So I now have 10 oxygen atoms. I put the dash there so you know it's not the number 100. And now let's see if I balanced it. On the reactant side, I have 3 carbon. On the product side, I have 3 carbon. On the reactant side, I have 8 hydrogen. On the product side, I have 8 hydrogen. Looking good so far. And on the reactant side, I have 10 oxygen. And remember, you got to add up all the oxygen from each molecule. I have 10 oxygen. It's balanced. Yay, we're done. And what that means is 1 propane molecule react with 5 oxygen to make 3 carbon dioxide and 4 hydrogens. Now, later in this chapter, I will teach you how important the coefficients are in a balanced chemical equation. Very important. So my advice is always leave hydrogen and oxygen to last. So I better share the fun. And if we look at at this chemical equation, this C5H12 is called pentane. It's a liquid, it's an organic molecule, and it's flammable. You react it with oxygen and a spark, it will burn just like propane. It's a minor constituent in gasoline, which we'll talk about at the end of the semester, and you get carbon dioxide and water. It's not balanced. You have to balance it. Your turn. Leave hydrogen and oxygen for last. And please be patient. We're going to try and give everybody time to finish. And I can drink some water that's hydrogen bonded. All right, everybody's finished. All right, I'm going to follow my own advice and leave hydrogen and oxygen last. So that means I start with carbon. There are 5 carbon. Ooh, there's only 1 and I need 5. So I'll put the coefficient number in front to 5. I have 5 carbons. Going this way, and I could have done oxygen, but I'm going to do hydrogen. I have 12 hydrogen. Oh no, I only have 2 here in the water. How do I get it to 12? 2 into 12 goes 6 times. So I now have 2 times 6, 12 hydrogens. And that leaves me oxygen. Here on this side, I have 2 oxygen. On this side, you count all the oxygen atoms and all molecules. 5 times 2 is 10 oxygen. 6 times 1 is 6 oxygen. And that adds up to 16 oxygen atoms. Well, how do I get 16 on this side? Well, oxygen gas has 2. 2 into 16 is 8. So now I have 8 times 2, 16 oxygen. And now I'm going to check, is it balanced? Here we have 5 carbons. Here we have 5 carbons. Here we have 12 hydrogen. Here we have 12 hydrogen. Ooh, looking good. Here we have 16 oxygen and use the total 16 oxygen and it's balanced. Yay. Now, let me remind you, if you can divide all the coefficients by the same number and get whole numbers, you should. It should be always the lowest denominator. There's another name for it. So if I were to have this, you could say, well, it's balanced. I've got 10 carbons, 10 carbons. I've got 24 hydrogen, 24 hydrogen, and I got 32 and 32. Oxygen, isn't that balanced? The answer is no, because I can divide each one of these coefficients by the number 2, and then I get this. Notice this one, you can't divide it by a same number and get whole numbers. Remember, when there's no number, the coefficient is 1. You just don't write it in. So remember, check to make sure you can't divide all the coefficients by the same number to get a different balanced chemical reaction, because this is wrong. Let's see, it even says on the screen. Oh, that was a bad joke. Sorry. All right, let's move on to a little more complex balanced chemical equation. I think I copied it down wrong. Hold on 1 second. I check something. Let me do a different chemical equation. All right, let's do this one. I'm going to do this one, and I have to find. Remember my advice. Leave hydrogen, oxygen last. So I have one aluminum here, but oh no, Al, two of them. I have two aluminum. So how do I get two on each side? I change the coefficient. And now I have two aluminum. Hydrogen, I'm going to wait till last. Sulfur, I have one sulfur here, but here, notice you have this bracket. Whatever in the bracket, you multiply by the subscript to the right, 3 in this case. So 3 times 1, I have 3 sulfur. Oh, I only have 1 here. How do I get 3? I'll change the coefficient. Let's do that again. I have 1 sulfur here, but here I have 1, but it's in these brackets. So you multiply it by this number, 1 times 3, I have 3 sulfur. And to get 3 here, I change the coefficient to 3. Now I've done aluminum, I've done sulfur. Well, all I have left is oxygen and hydrogen. So going this way, it doesn't matter which, I'll do hydrogen next. Here I have 3 times 2, 6 hydrogen. Here I have, well, none in this molecule, but I have 2 here. How do I get 3? Well, 2 goes into 6 3 times. So 3 times 2 is 6 hydrogen. And all I have left is oxygen. Here I have 3 times 4, 12 oxygen. Now remember, oxygen, you have 4, but you multiply it times the 3 because it's in the bracket there. And I have 12 oxygen there. Well, it looks good. Let's check if we balanced it. I have 2 aluminum, 2 aluminum, 3 sulfur, 3 sulfur, looking really good. 6 hydrogen, 6 hydrogen. I think we're almost done. Let's check. 12 oxygen, 12 oxygen. We're balanced, yes. So remember, leave hydrogen and oxygen last. And don't forget, when you have these brackets, this molecule here has 1 times 3 sulfur and 4 times 3 oxygen. And that's important. Now, I'm going to ask you to wait a second because I thought I had the right reaction. Let me find another one for you. All right. Oops. Just let me just do this better. All right, let's look at this one. You have aluminum reacting with CuSO4 copper sulfate, making copper Cu plus aluminum sulfate, Al2 bracket SO4 close bracket 3. And let me just make something even better. On a test, this would be printed out there. Your turn to balance this chemical equation. And remember, I would highly recommend you leave oxygen and hydrogen for last. In this one, there's only oxygen. Your turn. Wow, somebody's having a good time with balancing chemical equations. And it looks like everybody's done. So I better get to work. Now, if we look at this, I have one aluminum here, but I have two aluminum here. How do I change that? I now have two aluminum. Now here I have one copper, one copper. Well, I don't have to do anything, maybe. Here I have one sulfur, but wait, inside the bracket is a sulfur, one, but you multiply it by the number subscript to the right of the bracket, 3. So I have 3 sulfur. How do I get 3 sulfur here? I put a 3 in there. So now I have 3 sulfur. Now, how many copper on this side? It's changed. 3 copper. Remember, Cu is copper. If I only have 1 here, I've changed the coefficient to 3. So now I have 3 copper. And all I have left is oxygen. 3 times 4 is 12 oxygen. We have 4 in the bracket times 3. Remember, the coefficient here is 1, so we don't have to multiply it using that. 3 times 4 is 12 oxygen. I think I'm done. Let's check. 2 aluminum, 2 aluminum, 3 sulfur, 3 sulfur, 3 copper, 3 copper, 12 oxygen, and 12 oxygen. Yay! It's balanced. We're done. Remember my advice to you on this types of reactions, leave oxygen and hydrogen last. Now, there's one special case I now have to talk about, and that's what I call even odd case. What's even odd mean? Now here we have aluminum plus chlorine gas, Cl2 makes aluminum chloride, AlCl3. Now I have one aluminum, but here's why I call it even odd situation or case. Notice here I have 2 chlorine, here I have 3 chlorine. There's no number I can multiply 3 by to get 2. There's no whole number. Remember, coefficients are always whole numbers. There's no whole number here I could multiply 2 by to get 3. You can't. So what do? Well, you use Dr. White's even odd method. What's the number that both 2 and 3 go into to give whole number? Well, if you multiply 2 times 3, you get 6. And both 2 and 3 go into there because you multiply 2 times 3. So with that, I need 6 chlorine on both sides because 2 and 3 both go into that. I'll put a 3 here. 3 times 2 is 6. I'll put a 2 there. 2 times 3 is 6. But now we have 2 aluminum, and I have to change the coefficient here to aluminum. Is it balanced? 2 aluminum, 6 chlorine, 6 chlorine. I call that even odd because one side has an even number of an atom and the other has an odd. And the way I was able to solve that was, what number will both of these go into, can you divide into, to get a whole number? Because the coefficients, the number in front of the molecule or element always has to be a whole number. It's also known as exact number. And 2 times 3 is 6. Both go into 6. 2 goes into 6 3 times, and 3 goes into 6 2 times. So we now have our balanced chemical equation. And with that, I better give you one to try on your own. I keep on not giving myself enough space. Let me move this over. And this is iron plus oxygen gas, O2. And this is ferric oxide, or also known as iron oxide, also known as rust. And this is the reaction that causes your car body to rust if the paint job is not covering the metal. Now, your turn to do it. I see someone's really having a fun time. Wow, you people are really getting the hang of this. Let's take a look at this. Well, here I have 2 iron. I could put 2 in front of here, but I see here 2 oxygen and 3 oxygen. This is one of those even odd situations. And how do you handle this? What number does both 2 and 3 go into? Well, you multiply 2 times 3, 6, so it better do that. So if I have 6 oxygen here, I'll need to put a 3 there. If I have 6 oxygen here, I'll need to put a 2 there. But now 2 times 2 is 4 iron, Fe. How do I get 4 on this side? put a 4 in, and now I have 4 iron. And now, excuse me, I'm going to check. Does this go in? Does this balance? And now I have 4 iron, 4 iron, 6 oxygen, 6 oxygen. Yay, it's balanced. Remember, that's the even odd case. And also, don't forget, make sure you're not doing multiples, like where all the coefficients can be divided into by the same number to get whole numbers. You have to keep on doing that till you get the coefficients that can't be done, which is what I have in this one right here. Don't forget about the even odd, and don't forget my advice. When there's hydrogen, oxygen in the balanced chemical equation, leave those for last. Do everything else first. Makes your life a lot easier. If you don't believe me, try this one again when you're on your own and do the oxygen, hydrogen first. Yeah, you'll get there, but it's a lot more difficult. So, balancing a chemical equation, you write the equation using the correct formulas, which you're given. Determine if it's balanced. Balance the equation one element at a time, and then you've seen me check at the end, is it balanced? And we just did our practice time. Yay! All right, listen carefully. On test 2, I historically, I've got to write it soon because it's coming up in a week or two. But anyways, on test 2, I always put down balanced chemical equation problems. Usually I do 3 or 4, 3 points each. So out of a 100-point test, that's 9 or 12 points. Now, tomorrow's lab, let's see, is today Wednesday? I'll look on my computer. Yes, it is. Tomorrow's lab, you'll be doing balanced chemical equations. I'll go through this again. And it will teach you, by doing the practice, how to do that. Now, in that lab, some of the equations are already balanced. On my test, if I ask you to balance a chemical equation, you're going to have to balance it. I don't think it's right to say, well, it's already balanced. So on my test, the answer, it's already balanced, will never, ever be correct. I'll say it again. In my test, when I ask you to balance, to give you a problem, balance the following chemical equation, 3 points each, just like what we just did, you will always have to balance it. Don't ever put down, it's already balanced, because that's going to be wrong. You're always going to have to balance chemical equation on my test. All right, with that, it's time to move on. All right, this is one of my favorite areas, and it's the mole. Now, what is a mole? In chemistry, no, a mole isn't that funny little animal that goes underground and digs holes. No, the mole is the counting unit used by chemists. This is one of the most powerful concepts in all of chemistry, and it is. And so the mole, you should know the mole is the chemist's counting unit. Now, what do we mean by counting unit? Well, if you go to a supermarket and you go to buy eggs, you can't go in there and say, oh, I want to buy 1 egg. They'll look at you like, hold on while we call the police. You have some problems and they should help you. take you to a hospital. No, you can't buy an egg. They're sold by 12 in a carton, and those are called a dozen. Remember, a dozen is 12. Well, chemists use the mole as a counting unit, just like eggs are sold in a dozen, or if you go and buy bagels, you buy a dozen bagels, or if you go buy donuts, you buy a dozen donuts. A dozen is that counting unit. For chemists, they use the mole, and it's not the furry little animal that, hold on one second, I've never done this before. Great moments in chemistry, not. And and the mole is not in chemistry this furry little animal that digs holes in the ground. You can see it. No, the mole is a chemist counting unit. It's cute unless you fall into those holes. Quick, do I have time? Oh, I do. But first, let me finish up one thing. And the mole doesn't have 12 like a dozen. The mole has 6.02 times 10 to the 23rd units. And that number, 6.02 times 10 to the 23rd units, is called Avogadro's number. Avogadro is one of the most famous chemists, Italian chemists, who came up with concepts with the mole. And that's why the number 6.02 times 10 to the 23rd units, atoms, molecules, and other things, is called Avogadro's number, 1 mole. Now, two things I was going to tell you and I can share with you. One is that one year I went to overnight summer camp, and we get off the bus and we see this baseball field with all these American flags, the little ones in it. And we wonder, oh, wow, this is a patriotic camp. And when we got off the bus and everybody who's the buses, there are a number of us, arrived at the camp, the head of the camp talked to us and said, by the way, see those flags in there? We have a problem with moles. Those are holes, so be careful. We got to fill them in. Don't walk over there where the flags are. You might hurt your ankle. Now, that's one thing. Now, a mole is 6.02 times 10 to the 23rd. That's a huge number. And now it's time for me to say something very personal about me. And that is my birthday is the end of December. And the birthday gift I'd really love, really, really love, is 1 mole of pennies. It's just a mole of pennies. It's just pennies. If you figure it out, that's 100 million piles of pennies, and each penny has $1 billion or billion pennies in it. So it's 100 million times $1 billion divided by 100. That's a lot of dollars. That's probably more money that's been on our planet, is on our planet, or maybe will ever be. But it's just a mole of pennies. A mole is a huge number. And if I look at the clock, which I just did, I have one up here that I don't have to look at my computer one down here. It's time to say goodbye. Before I say goodbye, remember, hand in labs. When you hand in a lab, make sure you either include in your PDF file a selfie, picture yourself with something in the lab, or you can also do a separate upload. You can do more than one upload to any assignment and have your lab report and then your your picture, your selfie. Because if you don't, you get 0 points for the lab. I sent out some emails earlier today to students who forgot to do it for a couple of labs. And yes, you can still put it in. check your email. I think I sent you one, the person who just asked that. You know, nothing to be sorry about. It's a learning experience. If I was one of those mean instructors, oh, I'm going to give you a 0 and you can't change it. But I don't do that. I don't even go to the students. Wait, I just go only in jest. But it's Funny Humor Tuesday, Wednesday. Yep, it's Wednesday. But don't forget the hand in the labs. Don't forget tonight, I have my office hour from 7 to 8 p.m. Excuse me. And don't forget tomorrow morning, check your email. I will be sending out the password for test number 1. You'll download that from the assignment area, and you have until Friday, 4 p.m. to upload your answers as a single PDF file. And I have that in the email. I described that. With that, I'm done for today. I'll see you tomorrow. Don't forget, we have a lab tomorrow. It's balancing chemical equations. It's a quick lab. And that one, you don't have to do a selfie for it. But if you want to send a next picture of yourself to me, you can. And with that, I'm going to say, well, thank you. Thank you. Somebody beat me to it. This is a quick class. I'm going to say, Gang gesund. Remember, that's what my grandmother used to always say to me. That's in Yiddish, means go in health. And because of when the pandemic started and all the problems of that pandemic, I still do it. Gang gesund. Bye now. I stole that from Granny to Beverly Hillbillies. Bye.